Hello everyone and welcome to McLean 360. So in this video I want to solve a problem with you to illustrate the concept of axial loading and deflections. Alright, so let's read the problem together and solve it. So the aluminum rod ABC, so this is the aluminum rod, is having Young's modulus as 10.1 times 10 to the power 6 psi, which consists of two cylindrical portions of AB and BC. So AB is the first part, or the upper or the top part, and the down part is the BC. Now this is to be replaced with a cylindrical steel rod. So steel. And then the Young's modulus is 29 times 10 to the power 6 psi of the same overall length. So the key word here is that the length is the same. So the length of aluminium, or the ABC, even though we are going to divide it, but then the same material should be the same as the length of the steel. All right, now we are to determine the minimum required diameter D of the steel. So we want this diameter of the steel if its vertical deflection is not to exceed the deformation of the aluminum rod under the same load. So this is the same load, right? And if the allowable stress in the rod is not to exceed 24 ksi. So how can I solve this problem? Now the first thing that we have to do is that let's consider the deformation of the aluminum rod. So considering the aluminum rod, which is this rod, the two AB and BC. So let's say A for both aluminum sides A and B. We know that deflection is given by PL over AE. All right. So for the aluminum, it's going to be PL over AE for the first part AB plus PL over AE for the second part. So basically we are trying to say that the total deflection within this material will be that of AB plus that of BC. Okay, but they are all subjected to the same load, which is the same axial load of 28 KIPS kips, and then it is the same material, so the Young's modulus is the same. Therefore the P and the E will come out. So we have the length of AB divided by the area of AB plus the length of BC divided by the area of BC. All right, now let's put in the values and solve for so let's solve for it. Okay, so it's going to be okay, so the deflection in A will be the load, which is 28,000 psi, divided by the Young's modulus for aluminium, which is 10.1 times 10 to the power 6, and then divided by the multiplied by the length. So the length of the side AB is 12. So 12 multiplied by 4 divided by pi times d squared. So basically I'm trying to factorize out, I'm trying to put into the equation, the area. All right. Now the length of BC is what? 18 divided by pi multiplied by the area. I'm sorry, the diameter of the bottom part, which is 2.25 squared. So multiply by 4. All right. So in fact, we can even bring the 4 outside here, because it looks like 4 will multiply this and then multiply this as well. So multiply by 4. Okay. So here will be 12 and here will be 18. And pi will also, okay. So pi, so times 4 over pi, then we have this. So 12 plus 1.5 squared, 18 divided by 2.25 squared. So this is what we have. After getting this, let's put in the values and see what we will get. So let's pick our calculators and do it together. We will get 28 times 10 to the power 3 divided by 10.1 times 10 to the power 6 multiplied by 4 divided, oh sorry, let's do it again. 28 times 10 to the power 3 divided by 10.1 times 10 to the power 6, and then I'll multiply this by 4 divided by pi, and then into 12 over 1.5 squared plus 18 divided by 2.25 squared, and that gives us 0.031376 inch. Okay, so our deflection is 0.0 so 0.03136. okay, so that is the deflection in the aluminum. All right, now let's go back and look at the steel rod. Let's go to the steel rod and see. Now for the steel rod, the question, so look at the question. He said that we should determine what the minimum required diameter D of the steel if, so watch this, if the deflection, if its vertical deflection is not to exceed the deformation of the aluminum rod under the same load. So what does this tell us? It means that for the aluminum too, we are going to use the same load. Okay, all right, sorry, the same deflection and then the same load. So to find the diameter, it means that already we know the deflection. So it means that this, okay, so then given this, we can say that our area is going to be what? So our area will be PL over delta and then E. And then from here, he said that the same load, from the question, he said the same load. Okay, the same load. But then the idea is that the length here, which is the L, will be the L, which is the total length. So we just have to add 12 and 18. Then we divide it by the deflection, which we got from the aluminum. But the E is for the steel. So that one, we will use 29 times 10 to the power 6. Having done this, what will be the answer? Okay, so from here, our area will be what? So 28 times 10 to the power 3. Then I multiply this by 30, or let's say 12 plus 18, divided by 0.031376, multiplied by 29 times 10 to the power 6, and then bracket close. Okay, if I do this, I'll get 0.923. So 0.9232 inch squared. So this is the area of the steel, so that the diameter will be what? Pi d squared over 4. So the diameter will be the square root of 4a divided by pi. So then our diameter, so then d becomes square root of 4 multiplied by 0.9232 divided by pi. Therefore, our diameter will be the square root of 4 multiplied by 0.9232 divided by pi, and this gives us 1.084. But this diameter we have gotten is not the required diameter. Why? Look at the question again. He said that if the allowable stress in the steel rod is not to exceed 24 ksi, meaning that we cannot use that area we got and then that diameter, but we need to use that allowable stress here. Okay, so the allowable stress was given as 24 ksi. Okay, but we know that as for the load, it is going to be what? Under the same load. So that one is 28 kips. So since we know the allowable stress, we can say that the load divided by the area, then we can also say that the area will be the load over the allowable stress, which is what? 28 times 10 to the power 3, or divided by 24 times 10 to the power 3. Now the area that we get will be the required area, which will give us the required diameter. All right, because that is what satisfies the actual condition given. So it's going to be 28 divided by 24, which gives us 1.17. So 1.17 inch squared, and then taking the diameter to be square root of 4a over pi, we are going to get 4 multiplied by 1.17 divided by pi. And what is this diameter? So this diameter will be given by 4 multiplied by 1.17 divided by pi. Oh, sorry. So 1.22. So that is the required diameter, 1.22 inch. So this problem has been solved. Thank you very much for watching. So it means that this is the diameter that you are going to use, not this. Okay, all right.